Okay, Assalamualaikum and a good morning. So, let me continue for today's lecture. Let me just go to this. Can you see the lecture notes? Okay. So, more or less, we have come across this addition of two spins. So I already mentioned that one has to be careful the way it's been written down in certain books. Sometimes they just simply write this as addition of two vectors. But one should remember that the operators are going to act on a particular Hilbert space. So in other words, what happens in this case is the fact that the two spin being independent of each other, then one ought to have the tensor product of the Hilbert spaces of the individual spins. So that's why the structure of the operators is really a tensor product between two operators, one acting on the first Hilbert spin and then another acting on the other Hilbert spin, Hilbert space. Sorry. So we have done to a certain extent how to do this, and we've also made identification between two different kind of bases. One basis is essentially coming from the total spin, capital S, and then the M is the Z component of the total spin. So this will be essentially being given by these states 1 1 1 0 1 minus 1, and then there's a one extra state 0 0, and there is a correspondent in terms of numbers of the basis states. So in the case of the individual spins, you have spin up for the first particle and spin up for the second particle, and then so on and so forth. Okay, so in other words, from the individual spin basis, you have 4, and then from the total spin, you should have 4. So that amounts to having this 0 0 state on top of the spin 1 state. Okay. So we have seen how to do this. We are actually, so this is the claim that we had earlier. Okay. So one can actually identify the topmost state, spin up, correspond to spin 1 with Z component spin 1. And then the rest, one could actually use the ladder operators. Okay. So there will be a spin up, sorry, call ladder up operator, okay, and then ladder down operator, so given by S plus and S minus, which is going to be related to the S1 plus and S2 plus and S1 minus to S2 minus. So you act individually onto all these Hilbert spaces, and then you get the relationship between the two. Okay, so you have done that. I should mention, however, this is not the only way to do it. One could, here essentially we are doing it using step down ladder operator, but one could have started, for example, from the lower state, okay, from the lower state, and then use a spin up, step up ladder operator, okay, and then you get to the state 1 1 using that. Okay, so let me just leave this section on addition of two spins. Okay, the other thing that we had at the end of last lecture is how to build your 0 0 state. So 0 0 state is spin equals 0, the z component is 0. So remembering that uh, the, the eigenstate with different eigenvalues should be orthogonal. So in other words, if I take spin 1 state with m equals 0, okay, that should be orthogonal to that, and that should essentially fix everything with respect to the identification of the states. So this is essentially the orthogonal combination to the one of 1 0. So the 1 0 had a plus here, and 0 0 has a what you call a minus sign. So one of the things that one should also learn from this topic essentially about the symmetries of this state. So if you actually look, if I interchange your plus and minus here, and then consequently for this one, meaning I change the spin 1 and with the spin 2, so what will I have in this case? I will have this to be minus plus, and then this will be a plus minus. So in other words, it's related to the original state by a minus sign. So in other words, what one has in this particular case, that the 0 0 state is essentially antisymmetry under interchange of spin. Okay? And if you look at the case of 1 0, okay, so this, you remember this with plus, minus, plus, minus, plus, okay. Then interchanging spin up and interchanging spin 1 and spin 2 will just give you back the same thing. So in other words, state 1 0 and is symmetry under the interchange of spins, and state 0 0 is antisymmetry. So one can actually identify which is which. Okay. Whether when you say, suppose you measure the z component to be 0, how do you differentiate between the two states? Well, essentially that one can actually look at the symmetry of the spin interchange. Okay, and the other thing one should remember is the fact that for the case of spin 1, total spin 1, remember, let me just write it down here, is plus plus, and 1 0 is 1 square root 2 plus minus minus plus, and then 1 minus 1 is minus minus. It's not only 1 0 being symmetric, but you'll see that the state 1 1 and the state 1 minus 1 is also symmetric, because you interchange the two spins, you get back the same state. Okay, so sometimes this three states of spin 1, sometimes called spin triplet, and this one is called a spin singlet. Okay, and it's nice to see some application of this. In fact, the spin singlet and your 1 0 state is sometimes called the maximal Bell state. Okay, so essentially that's correlation between the spin up and spin down for those states. Okay, so let me just end it there, and then we start doing the formal theory in general. Okay, So in the case of the general case, you would actually have uh, a general angular momentum operator J1 and J2, where each J1 will have the three components. So J1I, J1J will have the commutation relation given by this, and similarly for your J2. Okay, so there are three operators here, three operators here. Individually, they are behaving like angular momentum operators from the commutation relation. And let's also assume that these two angular momenta doesn't interact with each other. Okay, so in other words, we will assume that the two J1 and J2, when they are taken the commutator, it will give you a zero commutator. In other words, you can actually commute these two operators. Okay. So with that assumption, one can now say that, okay, I can now build different Hilbert spaces for each of these J1 and J2, okay, because they are essentially independent of each other. Okay, and then one can actually get the addition of these two angular momenta operators to be coming from the tensor product of the Hilbert spaces of the individual angular momenta. So just like before in the case of spin, okay, then your additional angular momenta is actually given by J1 tensor product, the identity operator, and then the identity operator tensor product J2. So as we mentioned before, okay, of course the other one would also, this relation will also imply regarding its components. Then you can have your z component of your total spin given by addition of the z component of your individual, sorry, not spin, angular momenta, the addition of individual components, the z components of your individual angular momenta. Okay. So right, so now one could try to, okay, just like the case of the spin, one can start to build up with two different bases of the total Hilbert space. One is coming from the total spin itself. Okay, one would expect that the total angular momenta will have the same angular momenta commutation relation. So then one can use the angular momenta eigenstates of the total angular momenta. Okay, so and this can be done together with your J1Z and J2Z. Now, sorry, okay, this is the different option. I should go down here. So, yeah. Okay, sorry about that. I'm getting confused now. So, okay, so remember there are two different options in this particular case. One is to use the individual angular momenta eigenstates. So in this case, one should have, for example, J1 squared with J1Z, and then the other angular momenta J2 squared and J2Z. So in other words, your eigenstates will now be labeled by the individual magnitude of angular momenta J1, J2 together with the Z component M1, M2. So you have, for example, J1 squared acting on this state, okay, and it will give you a J1, J1 plus 1 H bar squared, and similarly for the component will have you M1 H bar. So remember what is really this state. Okay, this is really, okay, this should not do that. This state is really what? This is actually J1 M1 tensor product with J2 M2. Okay. So you have all this what you call relationship, the eigenvalue equation, so to speak, of this option of using the individual angular momentum. So they will form the basis. All possible combinations of this. Okay. So the other one is the one I mentioned earlier, which is using the total angular momentum, which is now given by J squared, okay, for the magnitude. Okay, so this is for squared magnitude of total angular momentum. And then, of course, the other one would be the Z component. Z component of total angular momentum. Okay. But then one should also supplement this in a way, because remember that the rule of labeling a state is to have the maximal number, the maximal set of commuting operators. So of course over here you already had the J squared and Jz, but then you also have your J1 squared and J2 squared to be commuting with all these what I call J squared and Jz. Okay, so in other words, one has that. Okay, the okay, this is a bit let me think, because yeah, okay, sorry, I mistakenly state that your individual component also commutes with J1 squared and J2 squared. It's only the J squared commutes with J1 squared and J2 squared. But if you do it for the case of J1Z and J2Z, they actually do not commute. Now, why is that? Is the fact that if we try to look at the J squared, how you form the operators. So these are coming from your J1 plus J2 dotted with J1 plus J2. And remember, these are essentially tensor product operators. Okay, so you will get this to be J1 squared, J2 squared. Okay, and then what happens over here, there are cross terms. Okay, so the cross terms, one can write it in this particular form. You have your J1Z and J2Z, okay? But you also have your J1 plus and J2 minus. This is coming from where? This comes from the X and Y. So because of these two terms, these two terms will not commute with the individual J1Z and J2Z, okay? So that's why you get the fact that it commutes, Jz itself will commute with J squared, but the individual components will not because of this term. Okay. Right. Sorry about that. So in this particular case, how we should label the eigenstate? Okay, one should label it using just using your J squared Jz, which is the normal way of identifying your angular momenta, okay, the state of angular momenta. But you also have your J1 squared and J2 squared as they commute with J squared, okay. Then this will also comes into the labeling of your angular momentum state for the composite system, okay. So remember, the rule is to find, okay, just to recall from the first course of quantum mechanics, the rule is to find the maximal set of commuting operators. To label the basis states. Okay. So in this particular case, you have your J squared, JZ, J1 squared, J2 squared. Okay. I think I mentioned something over here which I did not say earlier. These two sets have their name. Okay, the option one, which uses the individual angular momenta, is called an uncoupled representation. Okay, and then option two is option two is essentially called the coupled representation. Okay, and why it's named so is quite obvious. In the case of the individual angular momenta, you're treating your two angular momenta as being uncoupled. Okay, but in the case of the total, using the total angular momenta, your two individual angular momenta is actually coupled to each other. Okay. Right. At times, this is a very cumbersome kind of notation. Okay, for example, here I have J1, J2 to indicate the magnitude for individual angular momenta, and then a semicolon M1, M2. And for the coupled state, I use again J1, J2, semicolon, and then you have your J, the total angular momenta magnitude J, and your Z component of your total angular momenta Jm. So sometimes because of this cumbersome notation, one normally actually at any particular time, normally one has this J1, J2 to be fixed. Okay, then one can remove the label J1, J2 earlier, and then just simply say about Jm. Okay, so one use this instead, and then for the other case, remember the other one is essentially this M1, M2, and I can just write it as M1, M2. Okay, assuming that your J1, J2 is actually fixed. Okay, so most of the time in this particular set of notes, I will keep this to be written in full, but this one to be shortened. Okay, right. Now, one has to always to remember that the fact that you have two different possible options over here is just a matter of determining which set of commuting operators that you want to use. Okay, so the choice amounts to more or less saying that, okay, I'm just using a different basis. Okay, so the option one is using the individual angular momentum basis. The second case is using the total angular momentum basis, and from the the previous example about the two spins, and you know that the dimensionality of these two Hilbert spaces coincide, so I can actually form a one-to-one correspondence between the individual elements of your Hilbert space. Okay, so in other words, the Hilbert space is actually just describing the same physical system, but you have different representations describing it. Okay, and in the first course, one of the things that we had was, okay, one can pick up a basis, and then one can consider a different basis, and then the relationship between the two bases are given by a unitary transformation. Okay, so this we have actually learned by right. Okay, we have not, then you can look up my notes of the first course of the quantum mechanics, that going from one basis to another basis, one normally use just a unitary operator transforming it. Okay, so in the same way, one actually has this kind of thing also in the case of this additional angular momenta. Okay, the two different options that we had mentioned earlier, they are just different bases describing the same physical system of the composite angular momenta states. Okay, so in this particular case, one should think of, okay, there's a possibility to get from one basis to the other basis. Okay, for instance, one could take, for example, the basis in the total angular momenta states. Okay, and then I can simply operate this with an identity. Okay, and then this identity I will resolve in a different basis. So I use what? I use the individual angular momenta basis. Okay, so this will be 1 and 2, J1, J2, and 1 and 2. Okay, so I can do that. So I just insert this operator, identity operator in front, and basically what I've done, and when I resolve this identity operator with respect to these states, then what I have is essentially, I have this basis using the total angular momenta being expressed in terms of the basis of the individual angular momenta. Remember that this is a Borel ket, so this essentially is a scalar. So what I have now, essentially I have a sum of some coefficient over here multiplied by this basis using the individual angular momenta. Okay, so actually I have it down here, the resolution of identity. So in other words, this scalar thing, okay, is essentially the matrix elements of the unitary operator. Okay, and these matrix elements are, they have a name in the context of this angular momenta case. They have a name, it's called the Clebsch-Gordan coefficients. Okay, so they are really matrix elements of a unitary matrix. Okay, going from the coupled representation to the uncoupled one. Okay, and there are some properties one can actually impose onto this Clebsch-Gordan coefficient. Okay, one of the properties, of course, is this one. Okay. This is coming from the Z component. So the total Z component of the Z component of the total angular momenta must correspond to the addition of the Z components of the two individual angular momenta. Okay, one can think of this can think of it as adding two one-dimensional vectors. So they must correspond. Okay. Secondly is the fact, so in other words, this thing, okay, this Clebsch-Gordan coefficient must obey this. If it doesn't obey this, then it's going to be equal to 0. Okay. So whenever you have m not equals to m1 plus m2, then all your Clebsch-Gordan coefficient is just 0. Okay. And this can be proven over here, so you can just have a look at it. So I'm not going to say anything more. The other non-trivial property is the following. Okay. The other non-trivial property is the fact that your total angular momentum magnitude will have a range. Okay, you will have a range between J1 plus J2, which is the maximum value that you can have, but you can also have the value J1 minus J2, okay, the magnitude. Okay, like before, for example, S1, S2, S1 is half, S2 is half, and you see that, okay, I have the triplet S equals to 1, okay, triplet, which is correspond to S1 plus S2, and then the other one is S equals 0, which corresponds to S1 minus S2, okay, which just gives you the singlet. So in general, you have that property, but now in the case of the two-spin half, it's only these two combinations, but you can have more combinations with respect to this general case. Let's just take J1 equals to 1, J2 equals to 2, then the maximum one can actually have is essentially, the maximum one actually you can have is J1 plus J2, which is actually equals to 2, and then sorry, this is 1. Oh, never mind. So then I should have a different. If J1 equals to 1, J2 equals to 2, then this total angular momentum should be 3 maximum. Okay, and the minimum should be 2 minus 1. So J equals to 1. But in between these two, okay, there will be J equals to 2. Okay, because we remember that when you go from one level to another, it's always an integer change. Okay, even for the case of the half integer spectra, going from one level to another is going to be just an integer change. Okay, so you have that J equals to 1 to be the minimum, and J equals to 3 will be the maximum. Okay, and how do we actually prove this? Well, it's quite well. I mean, it's one of the it's just an algebraic computation. So you start enumerating all possibilities, but in order to do so, let's start with some assumption. One of the assumptions that we want to do, essentially, we want to say, okay, there must be one of the angular momentum having a bigger angular momentum from the other. Okay, so and then we fix that, and then once you fix that, okay, I know, for example, the maximum value of m will follow the maximum value of the J1 plus J2. Okay, so and that gives you the first information about the relationship between the two. Okay, so because you have m max equals to m1 max plus m2 max, and m1 max must come from J1 and m2 max must come from J2. Okay. The next step is to go lower. Let me see. Oh, what is this? Of course, the other thing that we should also have mentioned that M max must correspond to the J value. Okay, so in other words, if M max is J1 plus J2, okay, then your J has to be J1 plus J2. Okay. Well, actually, it's the other way around. I should say J1 plus J2 is the total J, and M equals to J1 plus J2. Okay. Let me just make sure that I don't say anything more, any more mistakes. I just need to check the next point. Sorry about this. Right. Okay. So the next thing is to go from this topmost state, okay, to the one below. So the one below should have one value less, no, or the value of your capital M should be J1 plus J2 minus 1. Okay. And how do you get J1 plus J2 minus 1? Can come from two different possibilities. So you can either have your M1 being, in this case M2 to be your maximum. So M2 maximum is actually J2. Okay. And then M1 is not the maximum. So M1 is now 1 unit lower. So that would be M1 equals to J1 minus 1. And then the other possibility is to swap the roles. So M1 is being maximum, so this is equals J1, and then M2 is not the maximum, so you have J2 minus 1. Okay, and the total of the what you call the total of your Z component will be J1 plus J2 minus 1. Okay, but now there is another complication coming from, okay, how do I get M equals to J1 plus J2 minus 1? What would be the value of J? Well, it can come from the case of J1 plus J2 minus 1. So in other words, in that particular case, that M that we had earlier will be the maximum. But we can also have the case of the other J's. Okay, and one has to enumerate all these possibilities, okay, to actually get all these different combinations. Okay. So let me go to the table. So the maximum degeneracy for a particular M eigenstate is usually given by this quantity 2J2 plus 1 degeneracy. Okay, so let me just do it by example, because putting everything general, then you don't actually see the pattern. Okay, so here's a table. So here is the case of J1 equals to 2, J2 equals to 1. Okay, so in this particular case, there are your J in this particular case should be 3, 2, and 1. Okay. So if I take, for example, the case of, what's the example that I had below? M value 1. So M value 1 is this one. Okay. And M value 1, if you enumerate all the different M1, M2, so this is the only combination. For example, 0, 1, 1, 0, and 2 minus 1. Other combination of M1, M2 will not give you capital M by right. Okay, this is taken from a book, so I should write this capital M there. So other combinations will give you a different M. Okay. And what is the total angular momentum state over here should come from these three possibilities. Okay. So for example, one should have 3, 1, 3, 2, and 3, 3. Sorry, I'm getting confused here. What I mean is the following. I want M equals to 1. So I have 3, 1, okay, 2, 1, and 1, 1. Okay. And how do they relate with this M1, M2? Well, that has to come from the operation of the ladder operators. For example, let me think. Your 1, 1 will have some kind of combination of this 0, 1, and 1, 0. The rest can have this thing coming in. Okay? So you really to find out what is the combination of the individual angular momentum states, you really need to use that property of the step down operator that we had earlier. I think, yeah, mentioned somewhere. No, maybe not, but let me just write it down. So one has to use your step down operator. For example, your total step down operator equals to J minus, and then this is multiplied, this is equivalent to J1 minus plus J2 minus. Okay. So in other words, in order to see what combination that you have on the using the individual angular momentum states, we'll have to revert back to the step down ladder operators. Okay. So you can actually see there are degeneracies over here. For example, here is only double degeneracy, okay, but you have a unique state which correspond to the highest state over here, 2, 1, that correspond to M1 equals to 2, M1 equals to 1, that should give your capital M equals to 3, for example, okay. And similarly over here is unique. So you can always see that the topmost state is unique, but anything in between will have some kind of degeneracies, okay, coming from the different J state here. Okay. See, and if you try to enumerate the number of the different states, then you'll find that you get that 2J2 plus 1 degeneracy. Okay. All right. And then if you consider, for example, oops, where am I? What did I do? If you consider, for example, the dimension of the total Hilbert space, okay, that should be equals to the individual Hilbert space dimension multiplied to each other. Okay, so this we have already mentioned earlier, but you can also see that the way we have done the above proof, you'll see that this can be done by looking at the degeneracy for each J state. Okay, so for each J state from the total angular momentum, we will have 2J plus 1 coming from the different M's, but your J is running from J1 minus J2, the smallest value that you can actually have, to the topmost value, which is actually j1 plus j2. Okay, and then remember the difference from one to the other should just be equals to 1, okay, an integer. So if you so this is just a arithmetic progression sum. So you can use the arithmetic progression formula. So you take the first term coming from the smallest value here, plug into j here, so you get 2j1 minus j2 plus 1, and then you plug in the topmost value, 2j1 plus j2 plus 1, and then multiply by the degeneracy for each of this particular j, which is given by the 2j2 plus 1 from the from the claim that we had earlier, but we have actually demonstrated that using an example. Okay, so then you'll find that simplified to what you need, which is 2j1 plus 1 times 2j2 plus 1, which is the thing that we had mentioned earlier, that the dimensionality of the bigger Hilbert space of the composite system is just the product of the dimension of the individual Hilbert space. Okay, so that more or less what I want to say. So perhaps at this stage, are there any questions at this point, or would you like to take a break? So this is a good place to have a break. Okay, let's have around 3 minutes. Is everyone back? Shall we restart? Okay, good. Right, so let me go back to the next notes. As I've said, all these things should be doable from the point of view using the step-down operators, but we are going to make things a bit simpler because these are conventions that has been taken in some way. As I mentioned earlier, your Clebsch-Gordan coefficients are just elements of your unitary matrix. However, one of the things that people do is to make your Clebsch-Gordan coefficients to be real. So in other words, what happens, you look at the Clebsch-Gordan coefficient over here, you know that if you swap these two, cat and bra, from one to the other, it should be a complex conjugate, but now you essentially make them to be equal. So in other words, they are real elements, or sorry, real numbers. Okay, so and a real unitary matrix is essentially an orthogonal matrix. Okay, and that helps simplify things a little bit. Generally, what happens in the general case is essentially you have phase factors. So in this particular case, we simplify that your phase factors are just simply equals to 1. Okay, it's a convention. Okay, and because of this, what happens in this particular case, if you take the sum, so let me rewrite this below. This sum I can originally comes from here. So the sum is over J and M. Okay, so the original sum is actually here. Okay, so really this is what this is, this bra acting on this cat, and then this being sum over this is actually sum over Jm. This is actually the identity operator. Okay. So in other words, what one should have is actually this mixed with that cat, and since it has different m values, so you actually have your delta m1 dash equals to delta m2 dash. Okay, so it's just a way of rewriting this equation really, but now the fact that you have this thing, you can simply think of okay, if the Clebsch-Gordan coefficient is given by this form, okay, I can always think of okay, this being the what you call the common label, so to speak, and that's being summed, and then here is actually a different labels, then I know that it's actually coming from this. Okay, so you have the orthogonality condition from there. So this is orthogonality condition. And it really comes from what? It's just your orthogonal matrix, really. Okay, and then if you rewrite it differently, instead of summing over J and M, here you sum over M1 and M2, so meaning the labels M1 and M2 over here should be the same, but the label for your J and M could be different. Okay, and in that particular case, it's the same thing really. You have really actually this Jm meeting with this J dash M dash. Okay, and that actually gives you that. Okay, so these are conditions that we need for the Clebsch-Gordan coefficient, and of course you also have this condition, which is the normalization condition. Okay, so really this is again from either normalization of your Jm, okay, in this particular case, and this being sum over. Okay, so then this is actually another. So this is with respect to some assumptions that people do take when they consider Clebsch-Gordan coefficient. The other thing is there is a recursion relation between all this Clebsch-Gordan coefficient, and this comes from your step up and step down ladder operators. So here is using the step up and step down operators acting on your Jm, but your Jm is now being resolved using your individual angular momentum states M1, M2 here. Okay, so one can actually use that, and then you find that okay, I have this relation times this relation. How best to think of this? Okay, this m plus 1, for example, just take the upper sign first, and then this is going to be related with the upper sign over here for m1, and then upper sign over here for m2. Okay, so really what you can think of this kind of I want to go to this figure. So you're really taking let me go back. See, I always got confused about this figure. So you have so when you do a J plus operator, so let's look at this vertices over here. So if you total the M1 and M2 values, so I get M1 plus M2 minus 1. okay, and similarly here. So when you do a J plus operator, okay, acting on these two states, I should get this M1, M2 states. But the way it's been done when you use this operator relationship is to see that, okay, when you act on this state of this by how should I say this? Your M1 and M2 states has to be realized from a J plus acting on this state as well as J plus acting on this states. I do not know how else to describe this. So essentially it's coming from this relationship anyway. Okay. And similarly for your J minus, so you have a different triangle. So if M1, M2 is here, so it should come from a J minus acting on this state and J minus acting on this state. Okay. So sometimes it's easier using diagrams to see what's going on. So you can have a plot now to think about what's actually possible to be done is to have a plot between an M1 values and an M2 values, and then you start building these triangles in to see the relationship between each other. Okay. So I think what do I want to show here? Let me think. So for example, just now, okay, I have the M1 and M2 values. Okay, that will have to be related with the total M value, but your total M value is now being reduced or being increased. Okay, so you get that thing that we had earlier. Perhaps this is not quite what I wanted to say. Let me think. Okay. So here's a plot. Here's a plot of M1 and M2 values. So sometimes what one can actually try to do is to see, okay, in this plot of M1 and M2 values, there will be this maximal state, okay, where M1 and M2 correspond to some value J, which is coming from your J1 plus J2, and then the most bottom state, which is coming from your minus J1 minus J2 for your M1 and M2. Okay, so you have this block thing, and then you have points, the vertices inside, which give you the different M1 and M2 values. Okay, so one could actually use this kind of diagram and then build up your triangles of your J plus and J minus to actually see what states can be connected to another. Okay, so essentially this is what I'm trying to say. Probably we will see this more in action when we look at the case of the spin angular momenta added to orbital angular momenta. Then this shape will reduce to a two row kind of thing. So and it's easier to think of that condition, what I call that condition for the case of the spin plus orbital angular momenta. So that is the thing that we're going to do next, I believe. So let's just think of what happens in the case of J1 equals to 1, J2 equals to 2, like the one that we had earlier. So there you have to actually see that, okay, for this you'll find that your J2 here, so that will be -2, -1, 0, 1, 2, and then J1 will be minus 1, 0, 1. So basically you have all those vertices coming in, okay, but then there will be some what you call states which correspond to the maximal given by this line over here, okay. So remember, this is just like a plot of M1 and M2, so this will actually give you a line, okay, corresponding to this condition, and then this another line giving this condition. So you have to build up, no, depending on the case of what is J1 and J2. Okay. We'll see this more later on. Okay, let's move on. Let's finish up this thing off. Another thing that people do is to define all this idea about Clebsch-Gordan coefficient using different symbols, really. Is the idea of a Wigner 3J symbol. So instead of starting from just J1 and J2, they will think of the addition of this J1 and J2 will give you a J3. So you can think of J1, J2, J3 is now sort of independent of each other, but because of the theory of addition, angular momenta addition, there will be constraint with respect to these values of J1, J2, J3. Okay. So the general formula for Clebsch-Gordan coefficient, I'm reluctant trying to prove this because it's difficult, but you can find the proof in some old papers. Okay, but this is essentially the general formula. Okay, you can find this in the paper of Raka. I'm not sure how we pronounce this. There are two series of two papers, Theory of Complex Spectra 1 and 2, and the paper is actually, no, it's quite old, okay, but they already did do this kind of what you call calculations explicitly. Okay, in those days we don't really have a computer or a table to do this. Okay. So I will probably not ask you how to prove this, okay, but no, it's supposed to be provable. So one of the things that people do is to define this Wigner 3J symbol, which is related to this Clebsch-Gordan coefficient here. Okay, so essentially the Wigner 3J symbol is sometimes called a symmetrical version of your Clebsch-Gordan coefficient. Okay, so instead of your Clebsch-Gordan coefficient, then one can write your what you call your coupled representation with the uncoupled representation in terms of the Wigner 3J symbols. Okay. Again, the concept is almost the same. If you get confused with this Wigner 3J symbol, just go back to the case of the Clebsch-Gordan case. Okay. And then what's good about the 3J symbol? There are some symmetries involved. Here is essentially one of them, which is the permutation symmetry. So you permute one of the column inside this this is not really a matrix, but no, this is really just the symbol for the Wigner 3J symbol. So you just swap these two columns, for example, there will be some phase changes. Okay, and the other thing is, if you flip the sign of your M1 and M2 and M3, okay, remember that your M1, M2, M3 will have also the negative version, and again you have this kind of the phase relationship between the two 3J symbols of this M1, M2, M3. Okay. There are some special case that is convenient for us to know. Is the case when J3 equals 0 and hence M3 equals 0. But that's quite easy. Then you can see that, okay, the total angular momenta is actually your zero angular momenta state. Okay? And that actually simplifies a lot of things, and is actually given by this formula. So all these things can be found in the book of what's the person's name? Ben and Avishai. Okay, Sakurai might not have it. Okay, but most of these things are actually tabulated. You can find this in some reference books, and normally people don't go proving this anymore because they can look up some tables. Okay, I think that's it for this particular lecture. Any question at this stage? So one of the things, apart from the general formula of the Clebsch-Gordan coefficient, which is probably a difficult thing to prove in general, but you can actually prove this when you have specific values of your J1 and J2. So that usually I don't take large values of J1 and J2. So one limits yourself to say J1 equals to at most 2 or 3. 3 would be already horrible, but no. But you need to know how to use the formulas for Clebsch-Gordan coefficient, and then also the Wigner 3J symbols, okay, with respect to the small values of your J's. Okay. There are some exercises given inside the book, so you can have a look at that. I will try to this is week 3, right? I've lost count. Week 3, yeah. So probably our according to schedule, I should have a first test earliest at week 4, so I should have one assignment coming up. Okay, for your first test. Probably maybe your first test will be week 5. In that sense. Okay. But don't worry. I mean, I'll give you some assignments so that you can more or less get the tools that you need to answer for the first test. I've yet to think about it. Okay, so thinking about this is also a problem. It's not easy. It's not easy even now. Okay, earlier I can think of simple exercises. I cannot do that now because it's an open book exam. So you cannot simply just copy and otherwise that would not test you. Okay, if it's a closed book, then I can just give you a bookwork that you have seen before. But now you must the technique you must be exposed to the technique, but then you have to apply it to a different problem. Okay? So there will be some combinations like going from you probably see in the notes going from the top state and down. Maybe I'll swap the order, going from the bottom state, going up, that kind of thing. So you should try to prepare yourself for that. Right. So now we should be going to the next lecture. So the next lecture is the one I mentioned just now, is to look at the case of a spin and orbital angular momentum addition, and this is particularly important because you do have those angular momenta in realistic systems, and you should be able to know that okay, whatever you get from the spectra in experiments will have to be arising from this kind of angular momenta addition. Okay, so this is so in other words, now we make it less general. Okay, from the formal theory case, okay, by stating that your J2 will now be the spin. Okay, so that settles one case. The other case is that your J1 is now your orbital angular momenta, and your orbital angular momenta has to be integer here. Okay, so that also puts some constraint with respect to the total angular momenta. So your total angular momenta, in other words, what would it have? it would have these two different possible values. Okay, remember that your values can range from j1 plus j2 until j1 minus j2, but there's on the two values of j2 that you can have. Okay, is so let's take j1 to be the bigger state. So the two values of j2 that you can have is just with one with the plus and one with the minus. So in other words, you have these two possible total angular momentum magnitude quantum number. Okay, and your L could be an integer which is greater than 0, and for integer L equals 0, which is a possibility, that means 0, essentially this would be corresponding what we call the chemistry notation, and it's called S state, right? Your S state is actually L equals 0 state. Okay, then your total angular momentum here is no longer two combination because there's no minus a half angular momentum. Okay, so you can only have a j equals to half. Okay, if you have bigger than the S state, for example, P state, which correspond to the P1 L equals to 1 state, okay, then you could have the two different things. So you can, that's why sometimes in some chemistry notation we have a P state which with an index with a 3/2 there, correspond to the L plus a half, and then a half there. Okay, so that is a combination of the orbital angular momentum and the spin state. Okay, so let's try to see what kind of Clebsch-Gordan coefficient they can actually have in this particular case. Well, from the step up and step down ladder operators, okay, so you can actually have the following. Okay, so this is stepping up the total angular momentum by 1, or going down by 1. Okay, and that amounts to either these two states, m1 plus 1 or minus 1, or m2 plus or minus 1 over here. Okay, this is the previous recursion relation. So we have not actually substitute all the conditions above. So if we try to do this on m1, m2 with the condition of the above, and you can see that m2 is now ms, your spin states, and your ms, there are only two different values. So in other words, I can have this row of plus a half state and another row of minus a half state. And then the number of what you call columns here depends on your J1, your L state. Okay. So as I mentioned earlier, you can now get relationship between what you call different M1, M2 states, okay, by applying your ladder operators. So if I start, for example, at the top state, okay, so here remember your earlier triangle. So in other words, what we have over here is I have this M1, M2 state. Okay, this can come from this M1, M2 minus 1, and then M1 minus 1, M2. Okay, so you have that kind of shape of the triangle for J minus. But now the fact that if I start on the upper row, there will be a missing state from here, okay, because I don't have states beyond m2 equals a half. So in other words, what I can try to do is I'll be able to relate points on this row using a j minus. And of course, you can do the same if you go to the bottom one. Then I would have this kind of triangle, which corresponds to a j plus. Okay. But these states are missing. So I can have your j plus relating all these points that give you the different m1 and m2 state. Okay. So what actually happens over here is that you have your recursion relation being simplified, giving you this particular condition. Okay, so this is coming from the top row. So you get this condition that gives you the state relating, let me see, m minus a half with the total state m. So this is like your, it gets confusing sometimes. So this is like your jm. Okay, so your m here must equal to m1 plus m2. So in this case, this will have to be what you call m minus a half plus a half, which is actually m, and that gives you that value m here. Okay, so you find that this Clebsch-Gordan coefficient will be related to this Clebsch-Gordan coefficient. Okay, so then I can start doing something easily for details. Okay, I have accompanying handwritten notes. Forgotten about this. Let me see if I have this or not. So that must have come from an earlier. Which handwritten notes that I have. Okay, no man. Okay, I'll figure out later on. But in other words, the details probably is, you have to do it yourself, I guess. But essentially, one can start thinking of going from the topmost see, this is j minus, so that means I go from the topmost state j minus. Okay, never mind. So you can see that this is just a rearranging of the first equation, and you can see what happens over here. Your m values gets increased. So in other words, your lower m value, so it's going from some point over here until it gets to the topmost. Okay, so one can iterate this in a way until you get to the topmost, okay, which is going to be m would be equals to L, so this is actually m. Okay, so you just iterate the formula that we had until it reached to the topmost. Okay, and then one has to fix something I think it's the normalization condition. Yeah. So when you fix this normalization condition, this to be equals to 1 because you have the topmost. So this is a dot M1 value, M1 maximum. This is an M2 maximum. And this state has to correspond to this state. There's no choice. Remember the previous picture that we had. The topmost state will not be degenerate and the bottommost state will not be degenerate. Okay, so the topmost state will have to correspond to each other and this has to be normalized and this will be equals to 1. Okay. Actually this is not really a normalization condition. This is just a convention. I could have actually used a different phase instead, but the idea here is to keep to get the most simplest convention and to essentially equate this. Okay. Easily I could have actually put a phase here if I want to, but no. The point is to have that simple correspondence for the topmost eigenstate. Okay, so in other words, I can include this so-called convention into over here. Okay, and then essentially I get my Clebsch-Gordan coefficient is given by this particular quantity. Okay, and this works for your orbital plus spin state. Okay. The only problem with this condition is now you're only remember you're only going from the top row. Okay, remember you start somewhere and then you go going from one state to another state here until you get the topmost state. Okay, so it is silent on what actually happens at the bottom state. So what one can actually do is to use another convention saying that, okay, whatever m that you actually have over here, okay, it has to come from the m minus half and half or m plus a half minus a half. Okay, the condition for a different J state, which is this is from the top row, this is at the bottom row, it should come from a similar combination. Okay, because you need to have the value m here, so that means you must have this combination again, must have this combination again. Okay, but the coefficient, what should you have over here? Okay, and in fact this also is an undetermined. Okay, I should also mention that. Okay, because y let me just oh sorry, this is not the Clebsch. This is just this state written in terms of this state and this state. Okay, the Clebsch-Gordan coefficient that we had is just known over here, and this is still unknown. Okay, this is still unknown because it comes from this ms equals to minus half state, which we have not dealt with. Okay, so in other words, what we're going to have, we have three unknowns coming into this picture. Okay, the Clebsch-Gordan coefficient that we have actually worked out is only this part coming from the top row. So what do we do? Okay, to find the other Clebsch-Gordan coefficient is to recall that the fact that your Clebsch-Gordan coefficient has to be an orthogonal matrix. Okay, because you assume that your unitary matrix is going to be consists of real what you call real elements, so it has to be an orthogonal matrix. So in other words, the orthogonal matrix for this kind of combination, you see that there are 4 different elements. Okay, 1, 2, 3, 4, and you can rewrite this as a orthogonal matrix like the rotation matrix, cos alpha, sin alpha, minus sin alpha, cos alpha, and then identify the cos alpha with the given Clebsch-Gordan coefficient. So you identify cos alpha equals to that, and once you identify that, then you can also get your sin alpha. So in other words, cos alpha equals to that amounts this one, this part should be equals to this part. Okay, so the other one will be sin alpha, but sin alpha can be obtained from the trigonometric identity. So you get cos squared plus sin squared equals to 1. So in other words, sin squared alpha would be 1 minus this, and then you can simplify that, and that corresponds to that. So in other words, your sin alpha will just be the square root of that. Okay. So finally, we get the full thing. So this is your cos alpha, this is your sin alpha, this is your minus sin alpha, and this is your cos alpha. So with that, I'm able to write now, okay, this is your coupled representation written in terms of your uncoupled representation with all the Clebsch-Gordan coefficients identified. Okay, and this is sort of easy to do because you only have that 2 rows of M2 vertices. Okay, if you have more, then you'll see that okay, you really have to think a bit more complicated than the one we have over here. So that's why for the general case it's a bit complicated, but I've already given you the general formula for Clebsch-Gordan coefficient. Okay, so that more or less sort of completes everything except the proof part. Okay, which is going to be horrible if I try to do it. Okay. The other thing that one can actually talk about is probably talk about the eigenfunctions instead of the states in terms of the cats and bras. So one talks about the spin angular function. Okay. So you will see that okay, in this particular case, you will have the two different components of your spinor function. Okay. It gives you a spin up component. This gives you the spin down component. And then the other part would be the spatial part. So the spatial part is given by your spherical harmonics. Okay, this spherical harmonics. But now one has to remember that your spherical harmonics over here is already inclusive of your this L and M here correspond to your spin plus orbital angular momentum. So in other words, I will, how should I say this? See if I have anything down here. Okay, probably if you don't mind, can we stop at this stage and I'll return back to this thing because I have to check what am I assuming over here. Do I assume L to be integer? I think L is integer and your M is having this half integer thing. Can we return to this in the next lecture? So I'll stop early today. Is that okay?
Sure, doctor.
So sorry about this because I was not really prepared for today's. Had something else to do. So let me just take the attendance. There's 5 people. Who's the other person? Oh, my presenter. Sorry. Okay. All right. Okay, it's done. Okay, I'll stop there for today, and thank you. Sorry for the shortened lecture because I really have lots of things on my mind at the moment. Okay. All right. Bye, and then we'll meet back on Thursday. Okay. Hopefully, by that time, probably figure out what's the thing for that part which I fumbled a little bit. Okay. All right. See you on Thursday then. Thank you.